Welcome everybody to a brand new day of Computer Science 41. Today we're going to be talking about Big O. We talked a little bit about this in the past. We're going to talk more about it now. Big O is one of the most crucial, most important parts of the vocabulary of computer science. If you ever go to like CPP reference, for example, and look up the vector, and you want to know how long does it take a vector operation to take place. For example, if I push back, how long does that take? If I push front, which doesn't exist, but if I did an insert or something, how long would that take? And so you can come through here and you can see, let's see here, where's insert? Insert, complexity, linear time. Yep. Constant plus linear in the distance between pause and the end of the container. So in other words, if you insert at the beginning of the container, then it's going to be linearly proportional to the size of the vector. So if you have n elements in the vector, if you want to insert something at the very beginning, you got to move everybody to the right one, and you got a million people in there, you got to move a million people to the right, and then you can insert your one. And so when you see these words here like linear, let's look at pushback. Where's pushback at? Where's pushback? There we go. Pushback is amortized constant running time, which means it averages out to constant running time, but not always. Sometimes it'll take longer. If we look at the constructor here, some of the constructors construct a vector in constant running time. Some of them construct a vector in linear running time, which means order n. So what does that mean? All right, so if we come to the server right now, like this, how about now? You guys got that? All right, if you guys see these words like constant and linear and things like that, what we're talking about there is something called Big O. In fact, that's order 1 is what we call constant running time, and order n is what we call linear running time. But there's other options as well, which we're going to go into today. So for example, if we have a vector of size n, pay no attention to that. If we have a vector of size n when we make it, n right now is 10 million, but that doesn't matter. Just imagine n to be the size of the vector. How long do you think it takes to create a vector of size 10 million? What do you think? If you made a vector of size 1, if you made a vector of size 10, if you made a vector of size 100, how long do you think it takes to make the vector? If you had to guess. I had order 1 there before, but that could have been a clever ploy on my part to throw you off the scent. Maybe I could do this in comma 420. So this is going to create 10 million elements in the vector, each one of which is going to be set to be 420. 4 seconds? No, I'm not asking about the time. Big O is much more nebulous and theoretical than that. Big O asks, as the vector gets bigger, does it take longer to do this? Does it take longer to make a vector of size 10 than it does to make a vector of size 10 million? Right? So we have Brandis guessing order 1 because that's what my comment was before. But the answer is actually this is order n, because it has to make 10 million integers and then set each one of them to 420. So n is the size of the vector. It has to do n operations. And an operation is sort of a nebulous concept, but if you want to think of like vector.at0 equals 420, that's an operation. Vector.at1 equals 420, that's an operation. Even though under the hood, you might be doing things like bounds checking and things like that. You can kind of thinking of it as just a single operation, even though probably the assembly is going to be much more than just one line of code. Okay, so let's talk about this. So if we're going to be adding up all of the elements in the vector, if we have a million numbers in the vector, how many additions do we have to do? If we have a million elements in the vector, assuming the optimizer is not going to optimize this away, which it might, because it knows all the values are 420. Assuming the optimizer is not going to come in there with its scissors and just give us the answer. If we have a million people in the vector, how many additions do we have to do? We have to do a million. Very good. If we have a billion, we have to do a billion additions. If we have a trillion, we have to do a trillion additions. That n there is how much work we do. The bigger the vector is, the more work we do. And this is a linear relationship. And so we call this order n. In other words, as n gets bigger, the time that it takes to do it increases proportionally. So if you have a million, things in the vector and it takes a second, then 2 million should take roughly 2 seconds, and 3 million should take roughly 3 seconds. These are not precise things. We're not doing timings. What we're doing is we're getting a feel for the slope of the curve. Like as our work gets bigger, how does time change? Does it change linearly? Does it change exponentially? Does it change logarithmically? Things like that. So it should be 1-to-1 in terms of additions. Exactly. Now, what if I said, how long does this take? Cout vec.front. This prints out the first element in the vector. This prints out the first element. It doesn't change it. It doesn't delete it. It just prints out the first element in the vector. How many operations does that take? Let's say that we have 10 million people in the vector, and we're just printing out the first one. What if we have a billion? Does it take any longer? No. Doesn't take any longer, right? So this is what we call an order 1 or constant running time function. So if we were to come back over to vector and search for front, I'd be very surprised if it was anything other than constant. Good. Who knows? Maybe there's something weird, but it is constant running time, which is order 1. Okay. But there are other options other than order 1 and order n, which is things we've both talked about before. So let me do this one. So let's say instead of the sum by itself, we are going to add, let's say we've got a million numbers, and we're going to add the first million up, then we're going to add up 2 to 99999, we're going to add up 3 to 99999, then 4 to 9999, and 5 to 999 over and over again. Okay. So we could write a for loop that looks a little bit like this. J is equal to 0. J is less than n. J plus plus. And technically, J is going to start at I. So the first time through the loop, I is 0, right? So the first time through the loop, J is going to be equal to 0, and it's going to do n work. The next time through the loop, J is going to be equal to 1, and so it's going to do n minus 1 work. So it's going to do n work, n minus 1 work, n minus 2 work, n minus 3 work, down to 0 work. Anyone know what the summation of 0 to n works out to, roughly? What's the integral of y equals x? Another way of putting it. How many operations is this going to do? If we've got if n is 1,000, how many operations are we going to do? First time through the loop, first time through the loop, first time through the loop. You were right, Brandis. The first time. First time through the loop, we do n operations. Second time through the loop, in other words, when I is equal to 1, we do n minus 1 operations. Because j starts at 1 this time and goes to less than n. Or if you don't want, let's just make it simple on you guys. Let's just make it simple. Okay, 0. Okay, we'll just do it. Second time through the loop, we do n operations. How many loops do we do? How many times does this loop? We do n operations n times. So this works out to be order n squared. Okay. And in fact, most of the time when you see an algorithm that looks like this, with this level of indentation, a nested for loop, where this one is 0 to n, so that says n times do n work. N times n is n squared. Can you guys hear me? Marsh, can you hear me? Okay. So you can hear it. Okay, cool. So what if we had a triply nested for loop that looks like this? So n times, it does n work, and each one of those n squared times, it does n work. So Garza, you're tripping. Is this blowing your mind? All right, let me maybe make it a little bit easier to understand. Garza, how many times is it going to print high to the screen? N squared, n cubed. How many times? N, correct. And then it's going to print high. Then it's going to print by. How many times is it going to print by after one high? It's going to print high once, and then it's going to print how many buys in a row? What do you guys think? Anyone? We print one high, and then how many buys do we get? N. Yeah, so there's N, N buys for every one high, and then there's world. There are N worlds for every one buy. And so it's going to do N times N times N work. And so this is order N cubed. Okay. So anytime you see a for loop that looks like this, like a triply nested for loop, as long as each one of these things is like 0 to N or something like that, then you're going to get a order N cubed thing. Does that make sense to you guys? So if N is 10, we do 10 times 10 times 10 work. Or 1,000, right? If N is 10 times, we do this loop. And then that loop calls this 10 times. And so it's 10 times 10 times 10, N cubed. You guys understand? If N is 1, it does 1 times 1 times 1. It will do this once. If N is 2, it'll do this 2 times 2 times 2. It'll do this loop twice. Each time that loop runs, it runs this loop twice. Each time that loop runs, it runs that loop twice. 2 times 2 times 2, 8. Okay. Anytime you see a triply nested for loop, your innate instinct should be to say that's an order N cubed for loop. The exception would be if the professor does a tricky and does something like that and puts like a 0 in there, or if they, I plus equals n, something like that, where like you're like screwing with the fundamental presuppositions of a for loop. But even this one, where I had j start at I, let's go back to n squared again. Even where I had j start at I, we were kind of working through that, right? The first iteration, we do n work, right? Because this is going to go from j equals 0 to j is less than n. That's n work. The second iteration, j starts at 1, so it does 1 less, n minus 1. And then the third is n minus 2. So the total work is going to be n plus n minus 1 plus n minus 2 plus n minus 3 ... plus 1. Plus 0 if you want to add 0 to something. So what is the summation of all numbers from 1 to n equal? Anyone know? Where's the multiplication coming through? This loop runs n times. So when I is 0, it's going to run this loop n times. When I is 0, it's going to do the summation here n times, because this is a for loop that runs n times. Then I becomes 1. And it runs this for loop n times, n minus 1 times. Make sense? So anyone know what the summation of all numbers from 1 to n is? No? 1/2 n squared. Okay. So is this a big O 1/2 n squared algorithm? No. We actually say it is order n squared. We do not care about things like, oh, it's 0.5 n squared. We do not care. We don't care. We don't. We don't. What we care about is the shape of the curve. As n gets bigger, the time is going to increase. The running time is going to increase quadratically. Okay. So if you multiply the amount of work by 10, you're going to do 100 times the work. Okay. If we had a triply nested for loop, if you multiply the work by 10, you're going to do 1,000 times the work. It gets slow real fast. Okay. All right, do you guys understand this? This is an n squared. The total number of additions you're going to do is proportional to n times n. N times, you do n work. Okay. Started early. Does that make sense? Stevie? Yeah, kind of. All right. Then let's maybe explain it one more way. See out. N is 10 currently. So n is 10. So how many numbers am I going to print to the screen? Started early. N is 10. So how many numbers am I going to print to the screen? It's a times table. Look at that. How many numbers are on the screen right now? 10 times, we printed 10 numbers. N squared. You see that? So 100 times, we printed a number to the screen because n is 10 currently. All right. N is currently 10. N is currently 10. So 10 times, it prints 10 numbers in a row, and it goes to the next row. So we got 100. N times n. Okay. Okay. So n squared, n cubed. All right. So let's get into something a little bit more interesting. Let's talk about log. How many people here remember logarithms from algebra? How many people here remember logs from algebra? They're like something like a tree, like wood or something comes from logs. I don't really know. I'm not a tree expert. So what we're thinking of big O is like, here's the size of the vector. As the size of the vector gets bigger, how does the time, I'm writing at a 90-degree angle, it turned out not bad. Okay, how does time increase? So if we have constant running time, it takes one operation to print the front of a vector, right? At size 1, at size 10, at size 100, at size 1,000,000, at size 1,000,000,000, at size 1,000,000,000,000. Order 1 never changes its running time. No matter how big the vector is, you can always print the first element in constant running time. That makes sense? For printing all the elements in a vector, it's going to have a linear relationship. So we call this constant running time here, constant. We call this a linear relationship. So if you want to print all the elements in the vector out, you're just going to go through the whole vector and print them all. So if you have 10 people in the vector, you do 10 units of work. If you have 100 people in the vector, you do 100 units of work. 1,000,000, you do 1,000,000 units of work. You guys understand? Like that's kind of, you know, oftentimes order n is as good as you can get because you got to parse the data, right? Like, you know, like you're going to be doing something, you know, and you got to open up a file that's got n data in it. You know, it's like that's the minimal, you know, that's as fast as you can get it because you got to look at it, you know. If you can do something constant running time, that's great. But like at a certain point, you got to open up the file and read all the data out of it. Okay, so then there is order n squared, and there's order n cubed, which I'm drawing with a little, it's not really to scale, whatever. That's order n squared, order n cubed. You can have worse, order to the fourth, order to the fifth. Those are really bad, you know. So if you have 1,000,000 people here, let's just go back to doing a summation again, I guess. Sum plus equals I plus j, something like that. Okay. So if we have 1 million elements in the vector, this is going to do 1 million times 1 million operations, which is 1 trillion. Right? So let's maybe shrink this down a little bit. It might take too long. So if we have 1,000 people in our vector, we are doing 1 million operations. It's order n squared. So if I compile this code now, it's got order optimizer level 1. So 287 nanoseconds, milliseconds, microseconds. Okay. Now if we turn this size up to 100,000, it's going to do 100,000 squared operations. So you see it noticeably is slower. So you see how the time just exploded like that? And then if we add one more significant digit there, and go up to 1 million squared, which is 1 trillion operations. So we'll run for a while. Okay. It gets more and more painful the bigger the vector gets. And 1 million's not even that big, right? 1 million's not really that many people, and it's already not fast enough for me, right? I am annoyed at how slow this is already. Okay. So logarithms. Logarithms are nice. So a lot of people don't really have a context for, you know, if you're at a party and somebody says, I changed the running time from order n to order log n. These are the kinds of phrases you will hear spoken at a party with computer science people. Okay. I was hanging out with my boy Moboy and some other people, and we were talking about, like, you know, what changes we wanted to make to Firefox, because Firefox had just been open source, Mozilla, you know, back in the day. And these are the kinds of words we use. We will just say, hey, I took it from order n time to order log n time. These are just the words that are part of computer science. You have to understand this lingo if you want to be, you know, part of the cool kids in computer science. It's just how we talk to each other. Okay, so is that better? Which one's faster, do you think? Order n or order log n? Which one's faster? A lot of students have no like conception for like what that means. What does log n mean? So let's go over logarithms real fast. So the log base 2 of 8 is 3. Okay. What that means is 2 to the x power equals 8. Solve for x. Right? So when we're trying to figure out what is the log base 2 of 8, what we're asking is, what is 2 to what power is 8? Okay. And so the answer is 3. So 3 is x. Okay. So let's go and just get a little feel for this. We're going to have x. We're going to have the log base 2 of x. What is the log base 2 of 1? So in other words, 2 to the what power is 1? 2 to the what power is 1? 0. 2. 2 to the what power is 2? 1. Okay. 2 to the what power is 4? 2. 2 to the what power is 8? 3. Good. 2 to the what power is 1024? 10. Okay. So if your program is given a vector of size 1024, and I tell you my algorithm will run out in order log n time, then that means I can solve the problem in 10 steps. So even though the vector is of size 1024, I can solve whatever problem it is in 10 steps or less. And if I double that, if I double this to like 2048, I only need one more operation. Isn't that cool? Every time I double the size of the problem, I only have to do one more step. And that's super cool. a lot of video game algorithms, like for example, you've got a bunch of objects in a world, things like that, and you shoot a line through it, and you want to know what did I hit. A lot of these algorithms can be done in log n time. So that means n is the number of objects in the world, right? And so if you have 1 million objects in the world, how many steps or less can I determine the point of impact? What do you guys think? What is a million? 1 million. What do you think? What is the log base 2 of 1 million? 20. What is the log base 2 of a billion? 30. Ish. Not exactly. And this actually is the reason why hard drives kind of lie to you. Okay, so have you ever heard of a gigabyte? Not a gigabyte. A gigabyte is different. A gigabyte is, let's see, this is 10 to the 3rd, 10 to the 6th, 10 to the 9th. A gigabyte is 10 to the 9th bytes. 10 to the 9th bytes of data. A gigabyte is 2 to the 30th bytes. And these things are not the same. Okay? They're close. Like you can see here, like 10 to the 3rd is 1,000. 1,000 is like pretty close to 1024. That's why we tend to use them interchangeably. But it's off by a little bit. So that's why when you buy your hard drive, they sell it in gigabytes, but your operating system uses gigabytes because they're powers of 2. And so when you reformat your hard drive, you buy an 8 terabyte hard drive, you get like 7.8 gigs. And you're like, what happened? What happened to the little fraction of a drive that I lost? And a lot of it is just because they're selling it in a slightly different unit system. So instead of 1,000, it's 1024. Instead of 10 to the 9th, a billion, it is 1.05 billion. Yep. So if the log base 2 of a billion is about 30, what is the log base 2 when you get 31? What is 2 to the 31st power? 2 billion. All right? Because we just doubled it. And how many integers are there? 32-bit integers. That's an int, right? An int on our system is 32 bits. So how many integers are there? What is the maximum range of integers that we can hold in a 32-bit number? 4 billion. It's not 3 billion, it's 4 billion, because every number you add here doubles, right? Every number on the right-hand side here doubles the number on the left. So going from 31 bits to 32 bits takes us from 2 billion to 4 billion numbers. Every number you add doubles, okay? So a 32-bit integer can hold roughly 4 billion integers-ish. Actually 4.2 billion and change. Right? Okay, so what kind of algorithm would be in log n time? I already told you one, doing like an acceleration structure where you shoot your gun and then the game tells you, oh, you hit a person. That could be done in order log n time. Another famous example of a logarithmic time, which we call order log n, would be a phone book search. Have you guys ever seen a telephone book before? Got like names in them and stuff. Illustration of a phone book. Years ago? Yeah. Okay. So, it might have been years ago, but when you were trying to find a neighborhood phone book, perfect. Yeah, let's say you're trying to find your friend Gunnar Lamar, okay? And he is in the phone book. Okay. There we go. That's kind of what it looks like. Okay. So, do you start at the A section and just start reading all the A's, all the B's, all the C's, all the D's? Is that how you go about finding somebody's name? If you did it that way, that would be an order n. That would be what we call linear search. Linear search would be start at AAA towing and work your way through Zebra cleaners or something, right? Start at the beginning, go to the end. All right. Nobody would search the phone book that way. Instead, we use something called binary search. Okay. So binary search says flip halfway. Open up the phone book halfway. If we're looking for Lamar, is Lamar to the right or to the left of wherever we split it open? We're like, it's to the right. Cool. We can then throw away, metaphorically speaking, we could rip out half of the phone book and throw it away and then repeat on the remaining phone book. So now we take the remaining phone book and say, all right, is Lamar to the left of here or to the right of here? And you're like, okay, I'm currently in the Sartorelli section. So L is to the left of Sartorelli. So I can rip my phone book in half and throw away, the right half this time. So all these guys get thrown away, and now you're down to, a quarter of the, you've only done 2 operations and you've already thrown away 3/4 of the phone book. And then you divide in half again and throw away that half. You divide in half again, throw that half away, divide in half again, throw that half away, divide in half again, throw that away. And you can find in 1 million names in a phone book, how many steps would it take you, ish, to find a name in a phone book? How many operations would it take you to find a name in the phone book if there were 1 million people in your city? Yeah, 20-ish. 20-ish. About. Yeah. Might round up, might round down. Yeah, whatever. We don't care. It's about 20. Okay. So, what's faster? Linear search, where you look for 1 million names, or 20? What's faster? Order n, 1 million, or login, 20? Yeah, login is ridiculously faster. Like, a lot of students don't really understand this. It's the opposite of exponentiation. Exponentiation is bad. If you had an order 2 to the n algorithm, every time you add one more thing to your vector, you would have to double the amount of work you do. Log is the opposite of that. Every time you double the size of your vector, if you go from a phone book with 1 million names in it to a phone book with 2 million names in it, you only go from 20 operations to 21. So you've just added 1 million more names. If it's sorted, if it's sorted, you've added 1 million more names and you only have to do one more operation. And then Fresno grows again and it doubles to 4 million. Okay, well now instead of 21 operations, we have to do 22. It's fast. 22 operations and you can find any name in 4 million in the phone book. It's pretty good. Okay. It's really, really fast. So a lot of students don't really have the intuition about logarithmic time. But logarithmic time, it doesn't go down, but yeah. Order log n, logarithmic time. Now there's a special one. There's a special one that is sort of here. Okay. And this is order n log n time. And this is called linear logarithmic, I think. Something like that. Linear logarithmic. And the reason why linear logarithmic is important is because this is sort. Sorting is one of the most common, most important things you can do in algorithms. For example, if you want to determine, if objects hit each other, oftentimes you'll sort them, geographically, sort them east to west, and then see if they touch each other. Quick sort, merge sort, heap sort, like Minkrelli's saying on chat. And sort is best case for random data. Sort is order n log n. Okay. Can you write a worse sorting algorithm that's slower? Do you guys know any sort algorithms that run in order n squared time? The sorting algorithm most students try to write when they start computer science is called selection sort or bubble sort, because they're 2 different algorithms. So if you have 10 elements, they'll go through the whole thing and they find the smallest one and they pull it out and they put it into an output array. Then they go through it again, find the smallest, pull it out, put it into the output array. So they do n work, then n minus 1 work, then n minus 2 work, then n minus 3 work. Order n squared. That's selection sort, that's bubble sort. Okay. Selection, sort. Bad. Don't use selection sort, don't use bubble sort. The bubble sort's okay if your array is almost sorted already, but in general, just use standard library sort because that one is guaranteed to be in log n. In fact, if we come up here and we search for sort, it'll tell you, it'll give you a guarantee of the complexity of the big O, speed, which again is a vague speed. It's not like milliseconds or something like that. It's saying that as the vector gets bigger, the curve is going to be proportional to n times the logarithm of n. So if you have n log n, there it is. Boom. Okay. Complexity, big O, n log n, right there. This is incredibly important vocab for you guys to know. So if you have 1 million people in your vector, how many operations does it take to sort it, roughly? You have a vector of size 1 million. You have 1 million names in your phone book. How many operations does it take to sort 1 million names? What do you guys think? $20? Trust me, you cannot do sorting faster than order n, because at some point you have to touch every element in the vector, right? Even just to see if it's sorted already. Like bubble sort, best case, has order n time, because bubble sort will just go through the whole vector and be like, oh, it's sorted already? Done. So bubble sort is really good if you're sorting a sorted vector. Bubble sort is amazing. It's great. Or if you have one element out of position in bubble sort, like if you have a sorted array and you're pushing back one thing, bubble sort's great for it. It will be an order n sort. It'll go and swap elements until the new guy is in the right place. So if you have a sorted vector that has one new element that needs to be put into its place, bubble sort is actually order n. But you cannot do better than order n. It cannot be 20 operations. 20 million, that's correct. So n log n, 1 million, n is 1 million, times log n. Log n of 1 million's 20-ish, whatever. Like I said, I don't really get hung up over, do you round up, do you round down? Base 10 on the calculator. Let's see here. 1 million, and we're going to log base to this. 19.9. Yeah. Whatever. It's 20. Okay. So there'll be 20 million operations. Okay. Not too bad. You can sort 20 million names pretty quickly, right? Like our computers run at 3 billion cycles per second. You can sort 1 million names fast. Okay. It'll take longer to print them out, than it will to sort them. You know what I mean? Okay. Is there anything better than order 1? Is there anything better than constant running time? What do you think? Negative. Order -1. It takes negative time. You finished the algorithm before you began. You send an email to yourself from the future to the past. Arguably, you can have order 0 time. If you work out what the math on Big O actually means, you can actually prove these are distinct. You have a tighter bound on the performance. So for example, binary search trees are a data structure that are always sorted. So sorting a binary search tree is order 0 because you can't. They're already sorted. You literally can't even call the line of code to sort a binary tree because it's already sorted. So this is kind of like a meme. Don't tell your grad school professors about order 0. They don't know about order 0. It would scare and terrify them. So I think mathematically, like, you can show you can have a tighter bound than order 1. If you get into the mathematics of how big O works, but yeah, most people don't recognize order 0. Okay, so the main ones you're going to encounter are these: constant running time, logarithmic, linear logarithmic, order n squared, order n cubed. Are there things worse than order n cubed? Okay. Are there things worse than order n cubed? Are there algorithms slower than quadratic, cubic, polynomial in general? Is there room in here for spooky algorithms to be super slow? What about order 66? It's treason then. Yeah, there are exponential functions and worse. So let me tell you guys about one of my favorite sorting algorithms. It's called Bogosort. So Bogosort is not an order n log n. It is not an order n log n algorithm. Also known as stupid sort. So for Bogosort, imagine you have a deck of cards. You shuffle it, and you see if it's sorted. If it's not, you shuffle it again and see if it's sorted. And if it's not, you shuffle it again and see if it's sorted. And if you're clever about it, clever about a very stupid algorithm, you can iterate through all the possible permutations of the cards in the deck. So, for example, if you have 3 cards, the cards could be 1, 2, 3, which is sorted, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. There's 6 possibilities, right? So one of those, so you just shuffle it 6 times, and if they're different every time, if you can guarantee you're going to go through every permutation of the deck, then congratulations, you will find eventually the sorted version of it. So while not sorted deck, shuffle deck. There you go. That is a heck of a sorting algorithm. And the best part is it works for very small numbers. Size 1, done. It's sorted. Yeah. Size 2 takes 2 operations. Size 3 takes 6. Size 4 takes 24. Size 5 takes 120. So the running time is exponential. Yep. So it is Bogo sort. Bozo sort, worst sort. So yeah, so there are definitely algorithms that are like pretty bad. Like that would be a order n exponential kind of thing, which is like, like that flies off the deep end real fast. Do you guys know the Fibonacci sequence? Is it? No, it's like multiplying. It's a factorial. Like factorial is often done recursively. So if you write a recursive function, oftentimes professors only have 2 algorithms they ever do recursively: Fibonacci and factorial, and both of them are terrible, by the way, to do recursively. Do you know how long it takes before you overflow an integer? Like if you're computing like 1 times 2 times 3 times 4 times 5 times 6, do you know how far you get until you overflow? When you pass the 4.2 billion limit on an unsigned integer? Anyone know? It's not. You don't even get to 20, I don't think. So we're going to go 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12 times 13, and we've overflowed. So it's like professors like have you pass an integer around, and And it's like, cool, your factorial algorithm is correct for 1 to 13. Out of all 4.2 billion possible integers, your factorial algorithm is correct for exactly 13 of them. Congratulations. Like it is literally like the worst, thing to do with an integer, because like you just overflow so quickly. That's how bad a factorial algorithm is, right? It's terrible. It is horrible. And so if you try doing BOGO sort, you can do it for 3 cards or 5 cards, but even by the time you get to like 20, you're talking about just ridiculous running time. Okay, do you guys understand that? Like this is like bad. Okay, and the most common kind of bad in terms of like running time is called order 2 to the n, or 3 to the n, and things like that. But 2 to the n exponential. This is called exponential.
Did you see my design?
I did. I like it. A bit of artwork for my daughter there. So exponential. A lot of students also, just like students have a hard time grasping logarithms. They have trouble grasping why polynomial quadratic is different, like intuitively. Order n squared versus order 2 to the n. Which one's worse? Which one's worse in terms of running time? What do you guys think? If you had to pick one, if you had to write an algorithm, you could either do it in order n squared time or order 2 to the n time. Which one would you pick? Ada, can you help me out with some algebra here? Come here. We're going to do some algebra with our students. So for 1, Ada, what is 1 squared? Just 1. What is 2 to the first power? 2. Look, it's faster. There you go. We're done. It's faster. Order n squared is faster. What are you guys talking about? Order 2 to the n slower. I'm kidding. Okay. For 2, we got a 4 here, and we got a 4. Look, it's the same. Okay, great. What about for 3? We got a 9 versus an 8. For 4, we got a 16 versus a 16. Am I doing the math right? I don't even know anymore. 25, 2, 4, 8, 16, 32. Look at that. It's just a little bit slower, right? 6, 36, 64, 7, 49, 128, 8, 60, 64, 256, 9, 81, 512, 10, 100, 1024. So that's not too bad, right? It's just like 10 times slower, right? It's not too bad, right? 10 times slower. Yeah, it doesn't just get bad. It doesn't get progressively worse. It gets way, way worse. So this progression, this exponential progression here, 2 to the first is 2, 2 to the second is 2. 4, yeah. So there's a famous story. Ada, have you heard this story before? There was a vizier that did a solid for a king, and it's probably not a true story, but it's fun. And so the king said, hey, I will give you anything you want, up to half of my kingdom, whatever, And the vizier said, all I want is for you to get out a chessboard. And on the first day, I want you to put 1 grain of rice on the first piece on the chessboard. The king's like, well, that's nothing. The vizier's like, but wait. On the second day, I want 2 grains of rice. And the king's like, all right, whatever, dude. Like, you've earned it. And I assume on the third day, you want 3 grains of rice. And the vizier's like, no, not 3. I don't want an arithmetic progression. I want a geometric progression. I want 4 grains of rice on the third day. The king's like, oh, that's not so bad. On the next day, 8. The next day, 16. Next day, 32. Next day, 64. Even on the 7th day, 1 weekend, you're only got 100 grains of rice, which is like, I don't know, like not even enough to go on, right?
I've heard the story, but like in like gold pieces.
With gold pieces, sure. So, how many squares are on a chessboard, Ada? Several. It's an 8x8 board. How big? How many squares are there? 64. So by the end of this geometric progression, we're going to be putting 2 to the 64th power rice grains on the chessboard. How many rice grains is 2 to the 64th power? Anyone? This is maximum long. It's a big number. Do you think that the entire Earth, Ada, has 18 whatever unit that is? That's a lot of rice, girl. See how much rice that is? It's a lot of rice.
Yeah, well, there's probably enough rice because a lot of people eat rice in India, in Japan, in China, and Korea.
You're going to create a black hole, I think, if you put that much rice on a single square of a chessboard. So, yeah, by the time you got to like day 10, you got 1,000 grains of rice. If you have more mass than you have to have mass at a certain density, and then you can compute the Schwarzschild radius where it collapses into a black hole. So you have to pack a lot of mass into a very small area to create a black hole of any significant size. Okay, so by day 20, we have 1,000,000 grains of rice. By day 21, if we have day 20 is 1,000,000 grains of rice, how many grains of rice do we get on day 20? Day 20 is 1,000,000. How many grains of rice do we get on day 21? You get 1,000,000 grains of rice on day 20. How many grains of rice do you get the next day? 2,000,000. How many the next day? 4. How many the next day? 8,000,000. Doubles every time. Doubles every time. Right? And so in the story, the king just chops the vizier's head off. He's like, stop. You're annoying me. So the lesson of that story is do not try to fool kings using mathemagical tricks. Yeah. 3 gallons of rice is 1,000,000. It's not bad. Not bad. We're at substantially more than 1,000,000 though. Right? By the end of it.
See, Dad, there's a lot more than 1,000,000, but I'm pretty sure we're way past that much grains of rice.
2 to the 64th? I don't think so. I don't think so.
How much? I'm gonna look it up.
All right.
How much rice?
How many grains of rice
It's
in the
787 million tons.
Okay. 787 million tons. Okay. In a ton. Let's run the math here, people. $14 million.
It actually says 2. Wait.
18 quintillion grains of rice.
See, there is that. Well,
is 2? Yeah, here we go. Is 2 to the 64th a lot of rice?
Yeah.
Is that a lot? They're running the math here. A kilogram contains 10 to the 5th power. A ton of rice contains 10 to the 9th power. So, a aircraft carrier. All right. To the 63rd power grains of rice is quite a lot, enough to feed 100 tons of rice to every single human on planet Earth. A kilogram of rice per day per human for 275 years. It is more than 1,000 years worth of rice production.
Hey, but there's definitely been more than 1,000 years of rice production.
Yeah, but we haven't been producing at our current production for a while. So it's a big number. It's a lot. So exponential is bad. And so the bad zone over here, it gets into what we call like intractable problems. So these are problems intractable. What that means is like if our algorithm requires an exponential or a factorial or, Lord forbid, worse algorithm, we're not going to be able to solve it for any problem of any size, right? If you have to do something where you have to like compute every possible combination of thing, it'll work for 3 or for 10. 2 to the 10th power is still only 1,000. But once you get up into 40, 100, like you're talking heat death of the universe to compute. Like 2 to the 100th power is an unfathomably large number. It's more than the number of atoms in the universe, and that's only 100. And so that's why doing things like chess, right? So for chess, a student looked it up. The maximum number of moves on a chessboard is like 200 something. And so if you want to figure out, if you're writing a chess computer and you want to figure out the best move, what you can do is you can look at every single move that you can make. If there's checkmate, like you're done. But Big O is always worst case, right? So with the factorial with BOGO sort here, sure you could get lucky and shuffle it right the first time, but with Big O you always assume you're doing the worst case. The last shuffle you get is the one that will be sorted. There are other things called like theta. That's a horrible theta, or mega. Sorry, there's a mega, and then there's like theta, things like that. And these guys are like best case, and like average case. We don't really talk about those guys. They're useful for other kinds of analysis. What is the best case running time for BOGO sort? If you happen to get lucky, what is the running time? Order what? Order what for BOGO sort? You shuffle a deck of cards, and if it's sorted, you're done. 1. Yeah, you could just get lucky. And that's what I used to tell my daughter when we'd go to like Chuck Chansey or something like that. Like, Ada, my strategy for slot machines is just to win the first time. Just to win the first time, and then we leave. Right? That's my strategy. Just best case, hit the jackpot on your first quarter instead of your last one. That's the winning strategy.
What if you actually did?
I did do that when Ada was like, I don't know, 3 years old or whatever. I'm like, watch. Let me demonstrate my strategy for you. I took out a nickel and I put it into the slot machine, and I won $20, which is like a 400 to 1 odds. And Ada was like, "How did you do that?" I'm like, "Girl, I told you my strategy. You put in a nickel, you hit the jackpot, you leave. That's my strategy at slots." And she was just like, right? Am I wrong? Like, I think that's a winning strategy, right? Just win the first time, right? For BOGO sort, best case. Sorry, it's not Big O.
Like that, like when there's like a robot playing against a boy, like in chess, the robot just like extended its arm and just like crunched the boy's hand.
Yeah, breaking your opponent's finger at chess does not fall under Big O. That's like big, ouch notation. Yeah, so the chess robot reached out and just snapped the finger of the boy playing him. That doesn't fall under this kind of analysis. But I can just imagine the chess machine saying, "You have 9 digits left." I see what Ada is saying. Okay. Best case. Okay. So you can't have a chess opponent. Yeah. You win at chess if the other person has no fingers left, right? You just automatically win.
Your students bot.
Yeah.
And the tic-tac-toe bot was just like cover up your old answer.
That was my bug. So I in CSI 40 a while back, I had students write tic-tac-toe. And so part of the assignment was you had to make an opponent that would always win if it could, or draw if it couldn't win. Right? It's a good CSI 40 exercise. And I had a bug in my bot, and my AI for it would move on top of your move. So if you took the centerpiece, it would just put an O on top of your X there. I was like, huh. So I'd take the corner and it would just move on top of the corner piece. And I'd take the other corner and it'd move on top of it and win.
Did you troll your students?
I didn't. No, I trolled myself. That was just a bug. That
trolled your students. Like, okay, guys, try to beat my tic-tac-toe bot. No, try to sync up your bot with my bot and see if your bot can win.
See which bot wins. My bot just moves on top of theirs every time. I was like, oh yeah, I forgot to add in a check for being full.
Oh, that's inconvenient. That's so sad. I want.
As long as you have two fingers in either hand, you can play chess. Yeah. Okay, so yeah, so chess. So the runtime of chess, right? Let's say that, let's just say that there's 30 moves possible on average at any time. You have to look at your 30 moves. And then for each one of those 30 moves, you have to look at the 30 moves the opponent can do. So if I move my pawn here, they can move here, 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 bishop here, 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 here. And then for each one of those board states, you can move 30 different ways. And then for each one of those, 30 times 30 times 30, 900, what was that? 27,000 board states or 2,700, whatever. So after 3 moves, you're already at like, I don't know, 30,000 possibilities. And then it's another 30 and another 30 and another 30. And so the thing is like, it's like order 30 to the nth power, kind of complexity. And is the number of moves out you're looking, and you're evaluating the board state at each one of those possible positions, trying to find out which one is best for you. Like maybe there's a checkmate in 7 that's guaranteed. And so you have to look at every possible combination. You don't have to, but you have to look at every possible combination of board state. Like, oh, that's the best one right there. No matter what my opponent does, they're going to get checkmated in 7. And the guy who invented, I think it was Dennis Ritchie. I think it was Dennis Ritchie. Ken Thompson. Okay, sorry. Yeah. So Ken Thompson is like one of the big heroes in computer science. So Bell Labs was like where a lot of the big advancements in computer science came from back in like the 1970s. And so, Bjarne Stroustrup was there. He made C++. He made Unix. That's kind of a thing that's kind of important. UTF-8, I hear that's important. He made kind of like the first chess machine, kind of. He's still kicking too. Like, he made Go, which is Google's new language. So let's go. Yeah. So, he's still active, I think. Since 2006, he's been working at Google. Yeah. And so anyhow, so he made a chess computer, and he had a big advantage over other competitors in computer chess. He said he hated playing chess himself, because either he wins and he feels bad about beating his opponent, or he loses and he gets frustrated. And so he got into computer chess, because then it's just like a technical problem. And so he had access to like these high-powered computers that other people didn't have access to. So his chess computers would like dial into a mainframe and have the mainframe solve chess board states for him. And so the chess computer got impounded, I believe. He was like supposed to like go to Russia or something, and like the State Department, I think, impounded it. So like computer secrets couldn't be taken to Russia. Like, it's fascinating. He's lived a really interesting life. It's very cool. B was language, yeah. And now we have C, and then after C is C++, then after C++ is C+++++, right? Right? There's C. C++ is C++, right? So, and then you have C+++++, also known as C#. And then there's also D, yes. Okay. So, I can't wait till we get to... No, there is an F already. Never mind. I was going to say, you can give your students, you get an F, but there's actually an F programming language. I've used it before. C*. Yeah. C double sharp. Yeah. Okay. So that's kind of like a good range of things here. Let me give you guys some tests. Let me see if you guys can look at some code and see if you can figure out what running time that code is. When I was at CPPCon in 2017, I took an Uber ride from the convention center in Seattle. It was held in Bellevue back in the day. Now it's in Denver, I think. And I took an Uber ride from Bellevue down to Renton, where a friend of mine was living. And along the way, my Uber app beeped at me and it said, "Would you like to take a test of your computer science knowledge?" And I was like, why is my Uber app quizzing me?
Is it just like when Google was like, "Why stop thinking about porcupines"?
It was something. Yeah.
Why was Google Maps? Why did Google Maps whisper in our car, "Stop thinking about porcupines"? If you weren't
listening
there,
in.
you would never believe it.
It's listening in.
How would it listen into mommy's thoughts?
And so what popped up? I'm like, sure, give me a quiz of computer science. And it asked me Big O questions. It had 3 questions on Big O. And I will see if you guys do as well. Okay, so what is the Big O running time of this? How many operations is this loop going to take? Big O what? Send your answers now. Oh, my tablet actually ended up landing on its edge. Perfect. Operators are standing by. Punch in your answers now. Started early. What you got for me? You're still typing. Oh, you erased it. Okay. Oh, stop typing again. All right. Order n is correct. Yes. This is an order n algorithm. Okay. What about this? Pretend each of these are I, J, K, L. I don't want to rewrite the I's. I'm not going to go through and edit all the I's to J's and K's and L's. Yeah, ordering court. So I was bouncing down the road. Like I was on a rough road in kind of the middle of nowhere in Renton. And I'm staring at this thing on my cell phone. And basically, this was a trick that I learned in grad school. I just looked at the shape of the code, right? If we have a quadruply nested for loop, then again, assuming the IJKs are not all I's. That's order in cubed.
Yeah,
Boom.
It's like you speak
Got it. It's a different language. Exactly, girl. This is vocabulary for computer science. When computer science people are at a party, girl, this is how we talk. Hey, I found an algorithm that my boss wrote that was order n cubed. Sorry, order n to the 4th. And everybody in the room would gasp. They're like, what? What? Order n to the 4th? What? Yeah, well, at least it's not exponential running time. You know, that's literally what computer science people sound like at parties. So when they talk to each other, which again, yes, you're right, Marsh, doesn't always happen.
Oh, I saw this picture.
Yeah.
Like this video was like find the programmer, and everyone else was like, and like had like very nice combed hair, except for one person he had like buttoned shirts. And they look very nice,
Yeah.
Except for that one person who had scraggly hair and wasn't.
The programmer is the guy with uncombed hair, a Slayer t-shirt.
And,
yeah.
And he had flip-flops.
What's the running time of it now? What is the running time of this loop there now? The same? I don't know. Are we doing any work? Nah. So it's n times n times n times 0. So maybe that was a little mean. I wouldn't normally give you a question like that. Okay. What about n times 0, 0?
When you give like your students a Greek apostrophe.
Oh, the Greek question mark? Did I do that with you guys? The Greek question mark? Was the semicolon? Yep. Yeah. So So an important thing, if I wasn't clear on that before, what is the running time of this algorithm? Does the running time of this algorithm increase linearly with n as n gets bigger? Does it increase with the square of n? Does it have a constant running time? What do you think? Yeah, it's order n. Very good. So some students would be like, well, this is obviously 2 times n. But no, we don't care about fiddly things like, oh, it takes twice as long. No, we don't care. It is just order n. Because what we care about, again, is that shape, is that it has a linear response time. So as n gets bigger, by some slope, we don't really care what the slope is at this level of analysis. This level of analysis is very high level. Because think about it. If you had 2 different bits of code, one ran in order in squared time, and one of them ran in order in squared plus 5 time. Like, let's put, I don't know, some cout time. When n is 10 million, n squared is a big number. Right? 10 million squared is a large number. If you add 5 to that, do you think you're going to notice anything? Right? Like, nah, not at all. It is trivial. It is absolutely trivial. And so I know some computer science people that will, but officially, according to the rules of Big O, you actually don't do that. Okay. Some people will also say, well, this is an order n cubed plus n squared algorithm. Again, this is just, if it's order n cubed plus n squared, it's just order n squared. It's just order n cubed. Okay? You drop the least significant terms because they're irrelevant, right? Because when you have 10 million, 10 million cubed is way, way bigger than 10 million squared. In fact, it's 10 million times bigger. So that extra term we had in there with the 10 million squared is literally, that guy right here is literally 1/10,000,000th the size of this. And that's only at 10 million, which is, again, not really that big a problem size. And so it's a trivial, insignificant amount of time added on to the whole thing. So we drop it. And there's mathematical reasons for that too. But basically, only the most important term gets reported. All the other terms we don't care about. Like, oh, well, we got a 5 on here. Great. We're doing 10 million times 10 million times 10 million plus 5. We don't care. That's it. Okay. All right. So let's give you another quiz. What is the running time of this algorithm? This line of code, just one operation, right? Sort. Just one command, right? Sort. What's the running time of sort? We went over this. Every computer science major needs to know the running time of sort. Best case for random data. You guys remember this? N log n. Everybody needs to know sort runs in n log n time. This is just something you have to know as a computer science major. Everybody repeat after me. Sort is order n log n time. Type that on chat, please. Ada, say sort is order n log n. Sort is order n log n. Say it again.
Sort is order n log n.
Thank you. Sort is order n log n. Best case. You can write worse ones. And I have. And if you have special knowledge about the data, you can do faster than that, like radix sort and things like that. But for random data, the best you can do provably is order n log n time. And that's honestly pretty good. It's honestly pretty good. Okay. Yeah, we'll stop there. That is Big O. Very, very crucial topic. We're going to be talking about it all this semester. Let me do one more example. All right. So if I were to merge two different vectors together. So let's say I've got a vector here, and it's got some data in it. 10, 20, 30, negative 40, 6, 6, 7, 7, 7, 8, whatever. And I've got another vector. So this is size n. And this one is size m. Got some data in it, whatever, 10, 20, 100, 111, 222, 333, 44, 00, whatever. How long would it take to combine the two of these into one vector? So let's say, we're just going to take all the elements of these and just push back them on the first one. How long is this going to take to run? To merge a vector of size n with a vector of size m. And we're sticking the second one at the end of the first one. We're not making like a new vector. What do you guys think? Order m is correct. This would be an order m merge. Okay. Yeah. Now, what if we were going to combine these two things into, like, you see how these things are all, well, they're not quite sorted. Let's say they're sorted, and we want to do what's called a zipper merge. And we're going to combine them together in a sorted fashion. So it's going to be 10, 10, 20, 20, 30. I don't even know what that is anymore. 40. You guys see what I'm saying? Like 10, 10, 20, 20, 30, 40, 100. What's the running time of that? We got a vector of size n, a vector of size m. They're both sorted, and we're going to combine them together into a brand new vector of size n plus m. You're always adding the smallest element in the vector. It is, in fact, very good. It is going to be order n plus m. Okay. And in fact, if we look at CPP reference, merged, n is, n is the sum of the sizes in this case. So n is the size of the first vector and plus the size of the second vector. So whatever, it's n plus n. Okay, all right. So yeah, you can have in Big O, you can have two different letters. Like if you have two different vectors of different sizes, then n plus m is something that you would see. Can we do better than that? Can we do better than n plus m? Or shall we say, let's say we wanted to just add all of these elements to the end here. Could we do better than m, all right, for the pushback version? And the answer is yeah, but not with a vector. So if you had something called a linked list, which is what we're going to be talking about next week. With a linked list, you have pointers connecting all of the elements of the linked list. They're all pointing at each other. And so the last element points at null, and the first element points at null. First element here that points at null, and the last element here points at null. And so you can combine lists together very easily. You just get the last pointer here, and the first pointer here, and you have this guy point at you, you have this guy point at you, and now you can merge two different lists together in order one time. Cool. So if you're doing a lot of merges, maybe lists are the right data structure for you. A little preview for next week. You guys understand? So Big O ties intimately in with the choice of data structure, because the choice of data structure is going to control how long all these different operations take, and so you have to find the right data structure for the task that you're doing. Make sense? That's why we care about all this. If you pick the wrong data structure for the job, your code will run until the heat death of the universe. If you pick the right one for the job, maybe it'll run instantly. Just kind of depends. Okay?